A single mismatched component in a utility system usually reveals itself through a high-pressure leak, sudden backflow, or a complete shutdown of the facility. Preventing this hardware failure means moving past vague emails to suppliers. You need a systematic approach to define your exact requirements, which we organize into a valve procurement matrix. This matrix isolates 3 distinct variables you have to solve before making a purchase: material compatibility, the internal gate mechanics, and the physical pressure constraints of your pipeline. We are going to lock in these 3 variables to build a highly specific request for quote, or RFQ. This document is what you will use to safely vet and negotiate with international manufacturers. By filling out this matrix, you stop gambling on the lowest price tier and start buying an engineered guarantee that the valve will hold up under your specific site conditions. Step 1 on the matrix is identifying the exact fluid or medium flowing through your pipeline. If the line carries water, gas, or light-duty oil, standard forged brass is the optimal choice. It is highly machinable, resists corrosion in these specific environments, and keeps costs down. Conversely, if you are pumping abrasive mining slurries or harsh industrial chemicals, those materials will rapidly chew through brass. You have to specify heavy industrial alloys instead to prevent the valve body from degrading. And if the fluid is potable drinking water, standard brass fails compliance. You must explicitly specify lead-free NSF 372 or NSF 61 certification to meet health and safety standards. With the exterior material set, Step 2 requires selecting the internal mechanism. This choice is dictated entirely by how frequently an operator will need to use the valve. For lines requiring fast, highly frequent shutoff operations, a quarter-turn ball valve is the engineering standard. A single 90-degree pull completely stops the flow. If the pipeline only requires infrequent isolation, staying open or closed for long periods, a gate valve is the correct choice, as it provides a straight-through path for the fluid. This cross-section shows a wedge gate, perfect for basic liquids, but high temperatures jam wedges, requiring parallel discs that slide without warping. For thick mining sludge, flat gates fail. You need a knife gate to physically slice the matter and seal. If you fail to match internal gate geometry to fluid viscosity and temperature, the mechanism will seize, regardless of how durable the exterior brass housing is. Steps 3 and 4 on the matrix lock in the operational space around the valve and the pressure thresholds inside the pipe. Space dictates your stem configuration. A rising stem threads upward out of the valve body as it opens. This is useful in open factory plants where operators need instant visual confirmation from a distance that a line is open. This side-by-side comparison shows the alternative. On the left is the rising stem, but on the right is a non-rising stem. Because it turns in place without adding vertical height, it is required for cramped utility closets and tight clearance zones. Next, check the pressure limits. Estimating these thresholds is a direct route to structural failure. You have to identify the absolute maximum pressure the pipeline will experience and ensure it accurately matches the PN, WOG, or SWP ratings published on the manufacturer's datasheet. Properly planning the spatial orientation around the valve also builds preventative maintenance into the system architecture. If the valve is oriented correctly within its clearance zone, a technician can safely access the seals or lubricate the stem threads without having to drain and dismantle the entire pipeline. This access is necessary because ball valves require routine cycling, and gate valves require regular lubrication to stop the internal threads from locking up over years of use. Specifying the correct stem height, proper clearance access, and precise pressure rating ensures the valve functions as an integrated, maintainable piece of your facility's infrastructure. Step 5 takes completed engineering requirements and applies them to the supply chain. Sourcing from the Chinese manufacturing market offers massive scale and competitive pricing. However, selecting a factory based strictly on the lowest price tier is dangerous. Unusually low prices often mask inferior brass alloys or missing legal certifications. To filter out substandard suppliers, attach a rigid 5-point vetting checklist to your request for quote. First, confirm the manufacturer possesses in-house precision CNC machining and forging capabilities, rather than outsourcing the core construction. Second, demand that 100% of the valves undergo individual leakage testing on the assembly line. Do not accept statistical batch testing. Finally, require the supplier to provide documented regional certifications, detail the exact specifications for their PTFE seals, and prove they have experience managing delivered duty paid, or DDP, shipping logistics. This rigorous factory vetting ensures that the exact tolerances mapped out on your matrix match the physical hardware that actually arrives at your job site. Look at the completed valve procurement matrix. You have locked in the fluid medium, the physical mechanics, and the compliance ratings. You started this process with a vague need for plumbing hardware. You now hold a highly specific, actionable engineering document. By combining precise material science, correctly specified internal mechanics, and strict factory vetting protocols, you protect your critical infrastructure from preventable leaks. Download the blank template below, define your pipeline variables, and send your engineered RFQ to a certified manufacturer today. In industrial utility systems, long-term reliability is not found by guessing on a supplier's website. It is engineered deliberately from the ground up.